We want to find the solution to the given initial value problem. The first thing we should recognize is that by looking at the differential equation given here, this is a linear second-order homogeneous differential equation with constant coefficients, meaning the given differential equation fits this form here where a, b, and c are constants. And because of this, we can find the general solution to the differential equation using a characteristic equation given here, where this is a quadratic equation in terms of r, and a, b, and c are the coefficients. So we'll first set up and solve the characteristic equation, and then discuss why the general solution will fit this form here. Notice a is 4, b is -8, and c is 3. So the characteristic equation will be 4r squared minus 8r plus 3 equals 0. And now we'll try to solve this by factoring. So if it does factor, it'll factor into two binomial factors, where the first terms here must come from the factors of 4r squared. The second terms of the binomial factors must come from the factors of +3, and then the sum of the inner and outer product must be -8r. So for the factors of 4r squared, let's use 2r and 2r. And then for the factors of +3, because we want the sum of the inner and outer product to be -8, we're going to use -3 and -1 for the factors of +3. So let's put a -3 here and a -1 here. Notice the outer product is -6r. The inner product is -2r, giving us a sum of -8r. So this is factored correctly. And now we can go ahead and solve, meaning if this product equals 0, then 2r minus 1 equals 0, or 2r minus 3 equals 0. So solving this for r, we would add 1 and divide by 2. R equals 1/2. Here we would add 3 and divide by 2. R equals 3/2. Now notice that the characteristic equation has two distinct real roots, and this tells us the form of the general solution will be this form here. So for a quick review, if the characteristic equation has two distinct real roots, this is the form of the general solution. If the equation has two real equal roots, this would be the form of the general solution. Notice how the second term has an extra factor of x here. And then finally, if the roots are complex, the general solution would take this form here. So it's important to remember that the types of roots from the characteristic equation do affect the form of the general solution. So for our problem, the general solution will be y, or y of x, equals c sub 1, some constant, times e raised to the power of r sub 1 times x. Let's call this r sub 1, and we'll call this r sub 2. So we have e raised to the power of 1/2 times x, or x divided by 2, plus c sub 2 times e raised to the power of r sub 2 times x, which would be 3/2 times x, or 3x divided by 2. Now because this is an initial value problem, we still have to find c sub 1 and c sub 2, and we can do this by using the fact that we're given y of 0 equals 2 and y prime of 0 equals 1/2. Notice how to use this initial condition. We will have to find the first derivative of y of x. Let's go ahead and set this up on the next slide. Now let's go ahead and find y prime of x. Notice we'll have to apply the chain rule here. The derivative of the first term would be c sub 1 times e to the power of x divided by 2 times 1/2, or 1/2 c sub 1 e to the power of x divided by 2. Then we'll have plus the derivative of the second term, which would be c sub 2 e to the power of 3x divided by 2 times 3/2, or 3/2 c sub 2 e to the power of 3x divided by 2. Now since we know that y of 0 equals 2, we'll substitute 0 for x into y of x and know the function value must be 2. So if x equals 0, we would have c sub 1 times e to the 0, but e to the 0 is equal to 1, so we'd have c sub 1 plus c sub 2 times e to the 0, which is just c sub 2, must equal +2. And now we also know y prime of 0 equals 1/2. So now we'll substitute 0 for x into the derivative and know the function value must be 1/2. So if x is 0, notice how this first term would just be 1/2 c sub 1. Again, since e to the 0 equals 1, so we have 1/2 c sub 1 plus, again, we have e to the 0 here, so plus 3/2 c sub 2 equals 1/2. Let's go ahead and multiply this equation here by 2 to clear the fractions. So we know that c sub 1 plus 3c sub 2 must equal positive 1. So now to find the values of c sub 1 and c sub 2, we're going to take this first equation here and the second equation here and solve this as a system of equations. So if we know c sub 1 plus c sub 2 equals 2 and c sub 1 plus 3c sub 2 equals 1, let's go ahead and solve this first equation for c sub 1. C sub 1 would be equal to 2 minus c sub 2, and I'll perform substitution into the second equation for c sub 1. So using substitution, we would have 2 minus c sub 2 plus 3 c sub 2 equals 1. So here we're going to have 2 c sub 2. We'll subtract 2 on both sides. That would be negative 1. So we know that c sub 2 is equal to negative 1/2. Well, now if c sub 2 is equal to negative 1/2, we can use this equation here. C sub 1 equals 2 minus c sub 2, which would be 2 minus negative 1/2, which is the same as plus 1/2. So c sub 1 equals 5/2. So if c sub 1 equals 5/2 and c sub 2 equals negative 1/2, we now have the information to solve the initial value problem. We'll substitute c sub 1 here and c sub 2 here for our solution. Our solution is y of x equals 5/2 e to the power of x divided by 2. And since c sub 2 is negative 1/2, we'll have minus 1/2 times e raised to the power of 3x divided by 2. And now to verify this, let's go ahead and graph this function. And since we know that y of 0 equals 2, this function must pass through the point 0, 2. Here's the graph of the function that we found. Here's the point 0, 2. And notice how our function does pass through the point 0, 2. I hope you found this explanation helpful.